Good evening, good morning, everybody. Today I'm here to talk about how CMS manage the dynamic pool. And I'll beginning the presentation talk about the CMS experiment and the submission infrastructure group. And then I'll talk how we exploit the traditional grid resources through HT Condor and Glide DWMS, and how we recently are starting to use more and more the vacuum model, what we call the vacuum model, to access non-grid resources. The CMS experiment is a high energy physics general purpose experiment that records proto-proton collision at CERN, and experimental data is stored, distributed, reconstructed, and analyzed in different data centers. We collect hundreds of petabytes of data per year. And traditionally, the data has been analyzed using the WSCG grid resources, the worldwide LHC computing grid, which is a collaboration of around 170 computing centers spread across the world. And access to those resources is done through pledges. And we have an increasingly number of contributions from HPC and other non-grid type of resources, which have a different model of allocation and have a different, are often opportunistic and volunteer, and have non-standard architectures, like there are multiple GPUs available and non-standard in the sense not 86, 64. And the group that takes care of providing these resources and gathering them in a central place that we call the global pool is the submission infrastructure group at CMS. We regularly organize HT Condor and Glide DWMS meetings. Because we are in charge of the operation of HT Condor and Glide WMS. And the global pool is the infrastructure where the reconstruction, simulation, analysis of physics data takes place. In this picture, you can appreciate the number of cores that we provide to the CMS collaboration that has been basically quadrupled over in the past 5 years. For what it concerns traditional grid resources, the way to approach to gather those resources and make them a seamless HT Condor pool is through the Glide WMS system. Glide WMS is a 10 years old tool that is a way to dynamically create an HT Condor pool and adjust the size based on the number of jobs that are idle in the various SCADs. And there's also a way to configure the start disk that runs on the grid. And the focus of today is to dig a little bit deeper into how this pool is created through Glide WMS. Everything starts with jobs appearing in the different sets of schedulers. We have tools used by individual physicists and tools used by a centrally small amount of people that are organizing the computing operation centrally. And we also have institutional SCADs that are where we allow jobs that are submitted locally to an external institution that are intended to run on that external institution. We allow those jobs to flock into the global pool and run on the whole grid. Jobs carries a set of requirements. There are the usual suspects like require memory, CPUs, and wall time. And there is a class site called the desired sites that list all the sites where the job is willing to run, and this is done for data locality, meaning that we prefer to run the jobs where data is present at site. The Glidin WMS frontend then looks at the pressure and sends Glidin request to the factory. There is a first matchmaking that takes place in the front end, where the requirements of the jobs are analyzed and matched to the resource present in the Glidin WMS factory, and then Glidin WMS requests are made. In the front end, we also specify specific CMS configuration, like the singularity, image, and bind mounts. We specify requirements to adjust the pressure of the idle job, because idle jobs and the idle jobs pressure in the scheduler is variable, and we accordingly adjust the number of requests we made into the various compute elements at the sites. We also configure the Condor in general, the Condor version. We want to run pilots, the slots layout, and other Condor knobs. Validation scripts to run on the worker node are configured also here. And we also maintain a different set of groups which carry different subset of configuration. Like we have a group for local user, where a certain set of jobs in the scheduler can be specified to run on extra pledge resources that are provided by sites, and we provide all the knobs in a different front-end group, so that because these jobs are configured, the pilots running those jobs need to be configured differently. We have groups for GPUs that requires different configurations, and groups for a group for overflow, where we allow under certain circumstances, we allow jobs to ignore the desired sites constraint and access data through XRD. The factory is then sending Glidin request to the compute element, and this is done through HT Condor G. So these are jobs in a factory scheduler, and the factory is shared across multiple experiments, and a set of configuration for the sites is statically maintained as a configuration in those nodes. Once Glidin eventually runs, we perform a set of resource validation, and for example, we run a number of scripts that were defined on the front end and are downloaded from the front end. We run script for platform selection, for singularity step. We run script to handle the draining of the node. So this means that we set up an HT Condor cron that run periodically, verify if the user, the sysadmin on the side has decided to drain the node. We have a custom start. We allow some sites to customize the start expression of the jobs running on their nodes. We perform this discovery of the CMS software and frontier, and if necessary, we set up the whole node, which means that we discover how many CPUs and how much memory the node where the Glidin is running, and we grab them all, and we provide a partitionable slot to that is of that size to the collector. This is because the final thing that Glidin does is to properly configure and launch a start diff that connects to the global pool. here we have an example with some stardies that are connected to the central manager, where we perform the second matchmaking. And this is where the central piece of the global pool, where all the resources from the grid are collected and made available to all the user job in a seamless way. We also have a non-standard set of resources, which has been growing in recent years, mostly because of the change in the funding schema that and the funding that is going through exascale infrastructure. In fact, HPC are one of the primary source of new resources. CMS access HPC through a different ways of through a number of ways. Help Cloud is the privileged way, where that is Help Cloud is a portal to an ecosystem of diverse compute resources. There is a talk in the next session about this. And this Help Cloud allows requirement, cost, and efficiency resources through glidings in a vacuum. This is when it's hard to put a compute element in front of resources, like some nodes that are network segregated. And we try to reuse the gliding framework for resource.
Hey Marco, we're losing a couple of sentences of
configuration as much as all developed. You have all these configurations. Excuse me?
We're losing a bit of your audio. Maybe I don't know if you have your video turned on, but maybe if you could turn off video, that might help. But we're just starting this slide. We've lost one or two sentences.
Trying to disable the video. Okay, so yes, so I was saying that we have the key aspect of accessing those resources, even if they don't have a C, is to reuse the gliding framework as much as possible and reuse all those validation scripts and all those scripts that configure the stardies that we have developed over the years. And let me try to. And this is done through this gliding in a vacuum technology, where gliding spontaneously start on the worker node, which means that are not requested by the gliding WMS front end, but started by a resource admin. And there is a tool we developed to generate the gliding command line argument that picks up the latest change, because we can have scripts that changes on the front end, and every time we do that, we generate a new file name that can be cached with squids, and accordingly the command line arguments of the gliding has to change. Additionally, we launch on some sites it's not possible to reuse this framework, but we still launch plain stardy. One of the examples is the split starter case at BSC, because the split starter are not supported yet in gliding WMS. And as said, in this case there is missing resource environment validation, and there is a need to maintain condor configuration as similar as possible to the one generated by gliding WMS, for example, because monitor tool relying on a standard set of resources. The HLT farm is one of the places where we use these stardies. HLT farm is the high-level trigger farm, which is a farm located through close where collision are taken in the detector, and is the farm responsible for doing the immediate computation on the events and selecting which events are of interest and which event need to be stored for later reprocessing. For run 2, we used a model where when the farm was used, we didn't access, and there was interfill period where we had full access to the farm, and then we had a period of time where there was a stable bin which was decreasing, where we had an increasingly number of resources available for the HLT that were connecting through the global pool, through native StarDs that were launched directly in the virtual machine. Virtual machine were allowed to be suspended in 24 hours. And in run 3, this old farm will be available total, most notably for offline, because there will be a new farm that will have the same model that will be used and will be replaced the old one for online, for the direct live processing of events. And this frees up something like 20K CPU cores for processing. And other opportunistic resource.
Hey, Marco, I'm sorry to interrupt, but we're running just a little short on time. Could you wrap up in a minute or two?
Yes, I'm trying to go as fast as I can. So this is another set of resources that uses the gliding in a vacuum. We have HPC attached to sites, and generally these resources are extension of fully pledged tier 2 centers that are integrated as sub-sites. Most of these resources includes custom start expression with additional filters to tune the matchmaking, because we don't want to run analysis job on HPC. We want to run the centrally managed job that are more well behaved, or maybe we just want to run Jensen job because no remote storage is required. So concluding, CMS Submission Infrastructure keeps expanding toward a more increasingly set of diverse resources. Non-86 architecture are also available. GPUs, we have started to use GPUs. There was a talk in this very same forum last year, which I'm linking here. And we are integrating all those resources while ensuring flexibility in the way we connect to the global pool. And this is the flexibility, the stability is especially important now that the Large Hadron Collider is restarting operations for run 3 from 2022 to 2025. There will be collision at an unprecedented energy level, and this is a time to accumulate new load of data for CMS and new territory for physics explorations. So future prospect, we continue pushing for higher scale we will continue pushing for a higher scale as required by CMS, and we need to also remain relevant by adapting our tools technologies to the changing technologies. And we have a talk next by Sakib that will detail how we completed the token migration for the global pool. That's all from my side.
All right. Well, let's thank Marco here, everybody.